Alright, in this video I'm going to show you how to create a trig function that has the given asymptotes, vertical asymptotes. Now, there are only 4 trig functions that we've talked about that will have vertical asymptotes. And those are tangent, cotangent, secant, and cosecant. Alright, those are the ones that have vertical asymptotes. We should be able to create any one of these 4 trig functions that have these vertical asymptotes. So let's play around with it and see what happens. Let's start with tangent function. Now, what we learned about tangent is if you consider one period of the tangent function. And here I'm just going to divide the period up into 4 sections. We learned that the tangent function begins and ends on the midline, but then there is a vertical asymptote right in the middle. So there'd be a vertical asymptote right here. Okay? Now, if we were to continue this pattern, then, alright, I could extend this for another period. So there would be another point at the end of this period and another vertical asymptote right here in the middle. Okay? So imagine that these vertical asymptotes are these 2 vertical asymptotes. 3 pi over 2 and 7 pi over 6. This would represent the period of the function. So for the tangent function, every asymptote, you have to go a full period to get from one to another. So if this is the period between 3 pi over 2 and 7 pi over 6, I should be able to calculate that by subtracting. So the period should be 7 pi over 6 minus 3 pi over 2. In order to do this, I need like denominators. So I'm just going to multiply these by 3. So that's going to give me 7 pi over 6 minus 9 pi over 6. Oh, okay, I kind of messed up because these must be, I'm getting a negative number when I'm subtracting, so I didn't actually realize at first. I feel stupid now because I should have known that 3 pi over 2 is actually bigger than 7 pi over 6. I was fooled by the 7 and the 3. So I'm getting this negative number because if you subtract, you get negative 2 pi over 6. Okay, so that tells me that I sort of have these backwards in the picture. Alright, I'm getting a negative number. So really, 7 pi over 6 is smaller. That should be over here. And really, 3 pi over 2 must be bigger. Okay, so if I switch this whole thing around, alright, this is better. I didn't want a negative period. So if I do 3 pi over 2 minus 7 pi over 6, like denominator, so that's 9 pi over 6 minus 7 pi over 6, I'm getting 2 pi over 6, which is pi over 3. So if I'm going to do a tangent function, which is what I'm working on, the period would be pi over 3. Okay, now the period does not show up directly inside of a tangent function. So the reason why I needed that was so I could find the b value. The period is always the regular period divided by the b value. So for tangent, the normal period is pi. So the period should equal the normal period divided by the b value. But this period is pi over 3. So that means pi over 3 should equal pi over b. Well, I don't need to do any fancy cross multiplying or anything like that. hopefully you can see that if I have pi over 3 and pi over b, guess what? b is 3. Okay, so fine. I have just discovered that b is 3. So that should be enough for me to draw. Well, is it enough? Not quite yet. Alright, I found the b value. I need to know the starting point of this point right here, because that's going to tell me the phase shift. Alright, that'll tell me the phase shift. So I need to know how big these are. I need to know what the coordinates of this point is. So we just found that the period is pi over 3. And I just found that the b value is 3. So I could find the any of these values that I wanted to if I keep in mind that every one of these marks is separated by a quarter of a period. So I'm going to do what I often do and calculate what is the quarter period. Okay, what is the quarter period? Well, a quarter period is going to be 1/4 of the period. So that's 1/4 of pi over 3. So that means the quarter period is pi over 12. So each one of these marks is separated by pi over 12. So that means if I subtract pi over 12, or I could add pi over 12, either way, I need to get to one of these pink dots, right? Either the first one or this one. I'll go ahead and shoot for the middle one. So I'm going to add pi over 12 until I get there. So if I wanted to add pi over 12, right, because that's a quarter of a period, that should give me this next mark. But I need like denominators, so I'd have to multiply by 2. Okay, so that would give me 14 pi over 12. And okay, so I'm taking 14 pi over 12 and I'm adding 1 pi over 12. So that's just going to give me 15 pi over 12 for this next mark. 15 pi over 12. And then the next mark over, which is the one I want, should be 16 pi over 12. Okay, so that should be this guy right here. But this reduces, so I need to do that. 16 pi over 12 reduces down to, let's see, dividing both of these by 4, that would be 4 pi over 3. So this point is at 4 pi over 3. So if I look at this as my starting point, like my first point of the period, normally for tangent we would start at 0. So if this is at 4 pi over 3, then that must be the phase shift. Okay, so now we have just found the phase shift. Alright, so the phase shift is positive 4 pi over 3. And that is enough for us to write the function now. Alright, so let's go ahead and do this. So armed with all that information, I now know that if I want to write a function for a tangent function, so I could just say y equals tangent. The b value is 3. Okay, so I would put a 3 in there. Now there's a phase shift coming, so I'm going to put parentheses. The phase shift is positive, so in the equation I have to put minus. And then here comes the phase shift, 4 pi over 3. Okay, and then close it up. We don't have to worry about an a value or a k value. We could just keep it right on the line. So this would be one answer to problem number 9 if we wanted to do the tangent function. Okay, so I feel like I should do at least one more. So I'm just going to put this up top. Let's see, can I just select it? Sort of. Alright, just lost its box, but that's okay. So that's one version of the answer. Okay, let's find one more version of the answer. Can we just remember one thing though? When I did 3 pi over 2 minus 7 pi over 6, that period was pi over 3. That equaled pi over 3. So that's just good to keep in mind. Okay, so basically the distance between these two, let's just save this for the next problem. The distance between these two is a distance of pi over 3. Okay, let's shoot for one more function. That took a long time, so I'm not doing all 4. Okay, I mean the cotangent function would be almost the same thing. Alright, let me just go in order, and I'll see how I feel. So if I wanted to make a cotangent function, what would I do? Well, we've learned that a cotangent function, if I wanted to do one period of the cotangent function, the cotangent function begins and ends with an asymptote. Alright, each period begins and ends with an asymptote. Okay, with one extra dot at the midline right in the middle. So this is sort of the pattern of the cotangent function. So with these asymptotes, and I've learned that now I know 3 pi over 2 is bigger than 7 pi over 6, so in my little diagram I'll put 3 pi over 2 over here and 7 pi over 6 over here. So just like before, these are separated by a full period. So again, so I don't need to redo all the calculations. So the period we found, if we subtracted these, we would get pi over 3. That led to a b value of 3. So that wouldn't change. So it's just the phase shift is the only thing that we have to worry about. So for this, it's actually easier because we could just say, imagine the cotangent function that just starts right here. The asymptote itself is the beginning of a period. So I don't have to do a quarter period or anything like that. I can just go ahead and just say, oh, this is the phase shift right here. Okay, so my phase shift would be 7 pi over 6. So my equation then for cotangent, well, an equation for cotangent would be y equals cotangent, and then there's my b value. Okay, this is positive, so I'm going to say minus 7 pi over 6. And that's it. That would be a cotangent function. Okay, now what about secant? Let's play around with that. I'll keep going. I'm a glutton for punishment. I'll just go ahead and do all 4. What the heck? What the heck? Alright, so let's do secant now. What does the secant function look like? Well, the secant function was based on being the reciprocal of the cosine. Alright, secant When I look at secant, I'm thinking 1 over cosine. So the first thing we would always do if I were going to draw a sketch of the secant function, or one period of the secant function, is I would draw a period of cosine function first. Okay, so a period of the cosine function would look like this. Alright, I have a point high, okay, and then it would go to the midline, and then low, and then back to the midline and high. So one period of the cosine function would look like this. Okay, but secant is the reciprocal of the cosine function. So anytime cosine is 0, that gave us an asymptote. So cosine, imagining for a moment that this is the x-axis, then these two values on the midline would be 0. So that's where we'd have an asymptote. So that's what we would usually do. We would say, okay, we're going to have a vertical asymptote at these two places, here and here. Okay, so we have these two asymptotes. Okay, so now we're supposed to say, all right, those two asymptotes, let's imagine that they are these. And remember that 3 pi over 2 is bigger. So this one would be the 3 pi over 2. And this one on the left would be the 7 pi over 6. And remember, we know that they are pi over 3 apart. We already know that. So here's the thing though. For this function, well, I guess I never really actually sketched the cosecant. So I feel bad about not doing that, so I feel like I should do something. So remember, for the cosecant function, we would go like this, and we'd come here and we'd go like this. Did I say cosecant? We're doing the secant function. Okay, so the green that I just drew, that's a schematic, a rough sketch of the secant function that we're working on. Anyway, these asymptotes are only a half a period apart. They're not a full period apart. They're only half a period apart. So remember, they are a distance of pi over 3. So that means that half the period is pi over 3. That's half the period. So in that case, the period must be twice as big as this. Alright? If half the period is pi over 3, then the full period must be 2 pi over 3. Okay? And if the full period is 2 pi over 3, then I should be able to use that little formula to find the b value. So remember how the period is always the normal period divided by the b value. Okay, and for cosine and secant, the normal period is 2 pi. So if the period is 2 pi over 3, then that means I'm going to have 2 pi over 3 is equal to 2 pi over b. Oh, look, I'm seeing a pattern. Alright, once again, if I have 2 pi over 3 and 2 pi over b, hopefully you can see that b is 3. That's what we got the other two times. Alright, so it looks like b is going to be 3 every time. Alright, so once again I have a b value of 3. So all I need now is the phase shift. This mark over here at the beginning is whatever that is, that's the phase shift, because this is the beginning of this period that we're sketching. So that's going to be the phase shift, this mark right here. Every one of these marks represents a quarter of the period. So the period is 2 pi over 3. Half the period is pi over 3. A quarter period, all right, I mean, if I go to the period, I mean, you should be able, a quarter period is going to be half of the half period. So the half period is pi over 3, so the quarter period is going to be pi over 6. Or, you know, if it makes you feel better, you know, the quarter period is going to be pi over 6. But I also could have said the quarter period is going to be 1/4 of the period. So 1/4 of 2 pi over 3. So that would be 2 pi over 12. But either way, you get pi over 6 for the quarter period. Okay, the benefit of that is if I want to find out what this value is, that's just a quarter period to the left. So I just need to subtract pi over 6. And I already have 7 pi over 6. So if I go down by 1, I will have 6 pi over 6, which of course is just pi. Okay, so the beginning of this period is at pi, not 0 like it normally would be. So that means pi must be the phase shift. Okay, so we have the b value and we have of 3, and we have the phase shift of pi. That's what we need in order to write the equation, the b value and the phase shift. So my secant function will be like this. Y equals the secant, and then here comes the b value, and now here comes the phase shift. This is positive pi, so I'm going to put x minus pi, and then there's my secant function. Alright, last one. It is time to do the cosecant function. Now, based on what we've seen over and over again, you can bet that the b value is once again going to be 3. So I don't need to recalculate that over again. Let's see, I'll use green this time. So we're doing cosecant, so I'm going to have y equals cosecant, and then I'll have 3, and then I'm going to have some kind of a phase shift. All I really have to find is the phase shift, because we've already seen that the b value is 3 every single time. Okay, so one more time, let's draw a sketch of cosecant. Cosecant is the reciprocal of the sine function. Keep that in mind. So basically, when I go to sketch one period of the cosecant function, I'm going to draw one period of the sine function first. Okay, so I'm going to separate this into 4 parts. And so my sketch of the sine function looks like this. So it starts on the midline, and it goes high, and then back to the midline, and it goes low, and then back to the midline. So this is my sketch of the sine function. Now, everywhere the sine function is 0, that's going to give us an asymptote. So start off by imagining that the midline is the x-axis, because that will let you know that the asymptotes should be here, alright, because if this is the x-axis, then this is 0. So I'm going to have an asymptote here at the beginning, and I'm going to have another one in the middle, and I'm going to have another one at the end. Okay, so I could pick any 2 of these to be the asymptotes that we want. Don't forget that the actual cosecant function would look like this. It would start from here and approach the asymptotes, alright, going away from the midline, and it would start from here down low and approach these asymptotes. All right, that doesn't affect our equation, but I just don't want you to think we're just graphing the sine function. Let's not forget that my sketch is cosecant. Anyway, back to the asymptotes. I definitely want to pick my first asymptote because that's going to be the phase shift. So if I let this first asymptote be the 7 pi over 6 value, okay, so if this asymptote is here at 7 pi over 6, and let's say that this asymptote is the 3 pi over 2, then I should be able to write the equation using 7 pi over 6 as the phase shift. Now, it just occurred to me that it does matter. I shouldn't have said that the b value is automatically 3, because that could change depending on whether I pick 3 pi over 2 to be my middle asymptote, or whether I pick 3 pi over 2 to be the asymptote at the very end. That's going to affect the b value. So I do have to think about it and recalculate it. Now, I think if I pick it this way, this is the same as what I did for the secant function when I only used the space between the asymptotes were only half of a period. So I think the b value will be 3, but let me just go through it again. If the distance between these two numbers, at the beginning of the video, we found that this distance, they are pi over 3 apart. All right, they are separated by pi over 3. So if this distance is pi over 3, so that's half of the period. So then a full period should be double that. So a full period should be 2 pi over 3. So if I were to calculate the b value, we know that the period is equal to the normal period divided by b. And if the period of this function that I sketched is 2 pi over 3, and then that should equal 2 pi over b, so b is equal to 3. So that's what I was saying before. Now when I'm finished, I'm going to go back and show you what would happen if I had picked the other asymptote to be 3 pi over 2. But let's finish this first. And really all I have to do is write in the phase shift. So this 7 pi over 6 at the beginning is going to be my phase shift, so I'm going to put minus 7 pi over 6. So that is one equation for cosecant. But I'm going to go ahead and write one more equation, because what if instead of using the middle as one of the two asymptotes we're supposed to have, what if I use this asymptote over here? Alright, which would be just easy to do based on the sketch. So there's no reason why I wouldn't. So this could be 3 pi over 2. That would satisfy the conditions. However, now in this scenario, we still know that the distance between 7 pi over 6 and 3 pi over 2, the difference between those is still pi over 3. That hasn't changed. All right, what's changed is that now this is the full period. It's not half the period anymore. This is the full period. So if I go back to that little equation that I always do when I'm looking for the b value, now pi over 3 is the entire period. So I would have to put pi over 3 here if I were to pick it this way. And now I would have to try to solve for b. And in this case, I would probably do the I would probably cross multiply. So along this diagonal, I'd have pi b. On this diagonal, I would have 6 pi. Then I would divide both sides by pi. and the pi's would cancel out, and I would have b is equal to 6. So in this scenario, that's what I would have. The phase shift would still be 7 pi over 6. Okay, but now I have a b value of 6. So that would be another version of the cosecant equation that I could make. I'm just going to create a little space for it. Alright, I'm running out of colors to use. Okay, I used all 4 of those. I'll just go with my gray color. So my final equation I'm going to write on this 30-minute video, goodness, is y equals the cosecant, but this time the b value is 6. So I would put 6 and then x minus 7 pi over 6 for the phase shift. Okay, so that's 5 different equations that we found. I found one equation for each function and then an extra one for cosecant. So I think 31 plus minutes is plenty for one problem. Don't you? It's a little ridiculous when you think about it. I hope it was helpful. I will see you on the next video.